Material 2, Chapter 1. In this chapter, you'll be learning about, actually 2 things you'll be learning in here. The one big thing is called proof by contradiction. Now, this is a very powerful method, technique, but also the hardest one to master about proof in maths. This is called proof by contradiction. I will explain a bit more later. But next part, 1.2 to 1.5, is about algebraic fractions, partial fractions. They all belong to a different category. So in this chapter, you've got two bits which are completely separate. So 1.1 on its own and 1.2, 1.5. Now, I would suggest you to leave 1.1 at the end of the chapter. So I will say you start from 1.2 and then up to 1.5. Once you're done with them, then you can go back to 1.1. 1.1 is a standalone chapter. I don't know why they put it in the first chapter, but it's probably one of the hardest one to master. Right, so proof by contradiction. So what it is? So first we have to explain what the concept is. Now in year 1, you learn through some proof techniques which are called proof by deduction. Right, you've learned proof by deduction. You have learned proof by exhaustion, which is doing one by one, and then you've also learned about proof by counterexample. Now these are very simple ones. And if you do further maths, there's also one called proof by induction. Now, in terms of level, these are sort of the basic ones. This is more advanced, and nowadays a lot of maths theorems which you wouldn't have learned a lot because they're really high level, university level. They are proved by contradiction, or they would be proved by induction. So these ones you've learned in year 1. They're not really useful in real life context. But anyway, so today we're looking at contradiction. So concept. Imagine we have to prove a statement that is true, all right? So we first have to assume, okay, we're going to first have to assume the statement is false. So we're understanding the concept in here before we actually apply into questions. And then what we need to do is we need to prove that statement would lead to a contradiction. Okay, will lead to a contradiction. Therefore, it is wrong to conclude the statement is false, and hence the statement is true. Now, let me show you something, okay? I'm going to show you a drawing of a cat. Okay, here's a cat. Wow. Here's a cat. Right, so what I'm going to tell you is I need to prove, okay, so prove that I am the best artist in UK. Let's not be too aggressive. Let's say just in UK. We're gonna keep in local UK or London. Okay, right. So what you want to do is, okay, so if this is a statement or proof, I'm going to prove that I'm the best artist in London. Then what you have to do is you first have to assume the statement is false. So what we do is we assume that I'm not the best artist. Okay, assume I'm not the best. All right, so that's my first step. Next step, I need to prove this statement is wrong. So I am going to assume I am not the best. I'm not the best artist, which is which is clearly not a fact. I'm not the best artist. Right, then we have to prove this statement is wrong. Well, to prove this statement is wrong is quite simple. This cat is the most amazing cat, best drawn cat I've ever seen. If you have any disagreement, you don't have to let me know. That's your opinion, which is always wrong. Anyway, so this statement, okay, so my drawing amazes everyone who saw. Okay, so that means this is proving this is wrong. So this statement is proving this is wrong. So assume that I'm not best artist is wrong because it amazed everyone, whether in a good way or bad way. So it's a masterpiece. It amazed everyone. Therefore, this is wrong. So if this is wrong, that means I'm not the best artist. In other words, I am the best artist. Okay, so that's the concept of contradiction. You assume that something is opposite, and you prove the opposite is wrong. Therefore, it is correct. So the structure of proof. We first have to assume. The first step, we assume. We have to put a. Now I'll put a open quotation in here means you will have to write this. You have especially the word assume. You must write the word assume. This word gives you marks. Assume, obviously, whatever follows has to be right, but without the word assume, it will be wrong. Assume that negation of statement. We'll come to this in a bit. Okay, negation of statement essentially means the opposite statement. It's called negation. Negation means a negative. Right, the second step. So maths reasoning to follow. So we're going to do the real maths in here. And then you're going to say this contradicts the assumption. Or you can simply say, oh, this is contradiction. Contradiction. And the last step, you will say, therefore, you reinstate the original statement. All right? Okay, so have this with you. We are going to continue. We'll have a look in the example. Example. Oops, what is this? What is this here? Okay. Example. Prove by contradiction that there is no greatest integer. Well, with the negation statement, so we have to use the word assume. Assume. Now, if you need to write one sentence that is completely opposite to this one, what would that be? I'll give you time to think. Now, to write a statement that is exactly opposite to this one. For example, now this is quite a debatable line. Prove me, Mr. Fan, is a male. Now, if you want to prove me I'm male, you wouldn't say assume I'm a female. That would be wrong, okay? Because nowadays we got, if it's not male, you might not be male. It might not be female. You might be trans. You might be different gender. So you will say, if I say prove Mr. Fan is a male, the negation statement will be assume Mr. Fan is not a male. Does that make sense? So it has to be directly opposite, which leaves no other ground of proof. So proof by contradiction, there's no greatest integer. Assume there exists a greatest, yes, English, who cares? A greatest odd integer, and we call this n. Okay, so n is the greatest odd integer. That means there's no odd number that is bigger than n. Right, so that's the first step, negation statement. Okay, step 2, okay, the maths part. Now, if n is odd, then n plus 2 is also odd, right? But we know n plus 2 is bigger than n because n plus 2 is bigger than n, therefore, contradiction, which is wrong. So what you're trying to do is you have proven the first step, the negation statement is wrong because this is not greatest integer. So third step, therefore, there is no greatest odd integer. Okay, so reinstate the original statement. Next one. Now, before we go to the actual proof, let's go into the learning the negation of statement. Now, the first part of proof by contradiction requires to negate the original statement. Think and discuss. If you're watching the video, you can have a go yourself, think about it, and then we'll go through the answer later. Think and discuss which statement should be the negation statement of each scenario. Pause the video now, have a go, circle your answer. I'll give you the answer later. And when you're ready, you can press play. First one, there are infinitely many prime numbers. So we will have to assume there are finitely many prime numbers. So this will be the correct answer. Okay, so we assume there are finitely many prime numbers. Right. The first one is not correct because you're proving infinitely many prime numbers. You don't care about infinitely non-prime numbers. You don't care about the other one because ultimately it's more about the prime numbers in here. The last one again, non-composite, you just sound off. Finitely non-composite is double, so the middle one has to be correct. Next one, all Santa Claus are costumed by men over 50 years old. Now, I would assume a lot of students will get it wrong based on my experience. A lot of students will have got it wrong for this one. Let me tell you which one is definitely wrong. The last one is definitely wrong. There's no such thing as known as Santa Claus because you're completely ignoring the fact. You're being ignoring the fact altogether. There's Santa Claus. There might not be. There might be. Well, don't break my dream. I believe there is. Right, next one. Now, this one. A lot of people will have put this one. No Santa Claus is costumed by men over 50-year-old. That's incorrect. Because in order to disprove all Santa Claus are men, you just need to have one. That is, actually, there are two conditions in here, men and 50-year-old. But let's say the main thing is about 50-year-old. You just need to find one that breaks the rule, which is not 50-year-old, then that will be enough to disprove the statement. You don't have to show none of them. Okay? For example, I would say, okay, I want to prove all students have done the homework. If I want to assume that it's wrong, I don't have to say assume no student did homework. I don't have to. So if there are 100 students, I don't have to assume all 100 did no homework. I just have to find one that did not do the homework. That's enough for me to prove not all of them have done their homework. Does that make sense? So in here, you just have to say there exists a Santa Claus who is less than 50-year-old. So there is one that breaks the rule. That's enough. You don't have to show everyone that is not. Okay. Next one, a last one. If it's drawn by Mr. Fan, it is a masterpiece. Well, period. Well, simple. This, trust me, this drawing, I'm going to name it Imagination. Let me write Imagination. You can't even write what it says. Imagination. Trust me, this will sell for millions when I die. Right, anyway, so if it's drawn by Mr. Fan, it's a masterpiece. Now, for this kind of statement, you can break it in two parts. The first part, this is called the condition. Okay. Next, it's a masterpiece. This is called the this is a statement. So this is the proving statement, or stuff you want to prove. Now, when you disprove something, when you do a negation statement, you never change the condition. Okay. For example, if it is raining, okay, if it's raining, no students go to school. No student goes to school. Now, but if you want to assume this wrong, you can't say if it's not raining, because if you say if it's not raining, then the whole thing, whatever comes out, is another scenario. You have said, if you want to disprove this, you will say if it is raining, there's one student go to school. Okay, so in here you will have to keep the front bit the same. If it's drawn by Mr. Fan, so if it's drawn by Mr. Fan, that's the only one that it is. Okay, it is. Then you disprove, negate the statement. It is not a masterpiece. All right. This is actually one of the hardest bits students will find when it comes to proof by contradiction. Right, next one. Example. Proof by contradiction that if n squared is even, then n must be even. So we mentioned about this condition. So there's the condition. This is the statement. When you do negation statement, you're only negating the second part. Okay, you don't negate the first part. So step one, assume if n squared is even, then n must be odd. Now you can also use the word non-even. Non-even also means odd because there's no, it's not like male and female. If you say non-male, it just means female. There's no third kind of number in here. It's either even or odd. So you can also say non-even, but we'll use the word odd in here. So assume there is, so if n squared is even, then n must be odd. Assume if n squared must be odd. Yep. Okay. So we're going to, second step, we'll do the math. We're going to let n equals 2k plus 1 because n must be odd. So what's the normal form of odd number? 2k plus 1, 2n plus 1. Any favorite letter apart from n? Thank you. 2a plus 1, 2b plus 1. If your favorite letter is x, 2x plus 1. So let n equals 2k plus 1. we want to find n squared, so we do n squared equals 2k plus 1 squared, which is double bracket. So n squared is 4k squared plus 4k plus 1. So equals to 2k squared plus 2k plus 1. And the reason I do that is because now I can show this is even. So because n squared equals even plus 1, therefore n squared is odd. Now, can you see contradiction? Because we assume n squared is even, but n squared is odd, therefore contradiction. Contradiction. And third step, if n squared is even, then n must be even. Okay? Right. Now, those are sort of the easier question that you see in exam. Now, one thing you shouldn't hate about this topic is because these proofs are never the same in exam, apart from 2 of them, which are known as a classical proof. Now, you will need to know these 2 classic proofs, 1 and 2. If they are asked in exam, they will be asked exactly the same. So that's a good thing. You can remember it, but I would suggest you to understand it first, and then you remember it. Now, I will start with classic proof 2 first, because proof 1 is harder. I'll do proof 2 first. Proof root 2 is irrational. Well, assume root 2 is rational. Now, you do have to write down the definition of rationality. We're all rational. Hopefully we are. So assume root 2 is rational. You will have to say, what's rational means? That is, now everything I write in here has to be shown in exam paper. That is, root 2 equals a over b, where a and b have no common factor other than 1. That means if a number is rational, that means it could be written as a fraction with no common denominator. For example, 4/5 is a rational number, or 0.8 is a rational number because it could be written as 4/5. 3 is a rational number because it can be written 3/1. Now, pi is not a rational number because pi cannot be written as a fraction. The closest fraction is 22/7, but even if you put 22/7 in the calculator, it won't give you the full decimals of pi. Okay, so therefore pi is not rational. Or any third form could not be rational. Reason being is they're not integers. Where A and B are integers. I forgot about that. Oh, they must be integers. Are integers that have no common factor. My mistake. Sorry. There must be integers as well. Okay, so it's not just the fact that they have no common factor. They must be integers. So therefore, now root 2 is irrational because root 2 you cannot write as a fraction. Now root 2/1 does not count because root 2 is not an integer. Right, enough. Let's go to the main deal. So how do we start with it? So we start with writing root 2 equals a over b. So I'm going to multiply b over. So root 2 times b equals a. Oh, actually, no, not quite. Actually, sorry. I need to get rid of square root, so I'm going to square on both sides to be going for my bet, sorry. So square on both sides, so root 2 squared will be 2, square a over b will be a squared over b squared. Now I'm going to multiply b squared left hand side, so 2b squared equals a squared. I'm just going to flip left and right, so a squared equals 2b squared. When a number equals 2 times something, it means a squared is even. Because a squared equals 2 times something, so a squared is even. If a squared is even, a is also even. Think about all the even square numbers. 4, 36, 64, 100. When you square root them, the square root number must also be even. Because 2, 6, 8, 10, you can see. Right, so where am I getting it? Next, so if a is even, what can we do then? If a is even, then we can let a equals 2c, because even number means 2 times something. Like 2k, you can use 2k. Let a equals 2c. So if a equals 2c, we carry on from here. 2c squared equals 2b squared. Square both. 4c squared equals 2b squared. Divide by 2. 2c squared equals b squared. Oh, what happened? So it means if I flip left and right, this step is optional. B squared is 2c squared. Therefore, b squared is even. And therefore, b is even. So what is the problem then? The problem is that we said a and b should have no common factor other than 1. But what have we shown in here? A and b are both even. So, therefore, contradiction. Now, this what I write in green is, you don't have to write down. Okay, contradiction, just for your understanding. Because A and B have common factor of 2. Okay, so you can use a pencil to connect them here, connect the dot for yourself. So when you do revision, there, you should understand where this line come from. So therefore contradiction. Therefore, root 2 is irrational. All right. Now let's go back to classic proof 1. This is the one that students find the hardest to understand what's going on in here. So now this is a very famous proof, and that's why you call these people genius, because you'll never see where they're coming from. Now this done by a very famous Greek mathematician called Euclid. You might have heard of him. You might want to Google him, but he he has a lot of things to do with very high level of maths later on. It lays a very good foundation of mathematics for nowadays. Right, so proof by contradiction that there are infinite amount of prime numbers. So negation statement, assume, so the opposite infinite is finite. So there is a finite amount, of prime numbers. So what are prime numbers again? 2, 3, 5, 7, 11, 13, 17, 19, 21. Oh, 21 is not. 23, 29, 31, 37. I'll stop there. There's a finite amount of prime numbers. We call them P1, the first prime, P2, P3, and Pn. Okay, so now what I write in green is you do not have to write down. Okay, so that's the first prime, just to make you aware. First prime, second prime, third prime, and this will be the last prime. Now we said there's a finite amount, therefore there must be the last prime. Okay, so there's a finite. Now we don't know what n is. Okay, what we assume is there is a list. There's an n to this list. Okay, so this is the full list of prime P1 all the way to Pn. Now Euclid, this genius, has done a very special trick in here. That's trick in here. So we're gonna let x be a number such that x equal, he multiply all these prime numbers, P1 times P2 times P3 times all the way times Pn. And then after that, he add 1 at the end, add 1. Now, why is this genius? Okay. Now remember what we're trying to prove. We're trying to prove there's a finite amount of prime numbers. So this is what I'm going to show you, the number version. So before I carry on with the proof in here, I'm going to show you the number version. Okay, so I'm going to write, again, you don't have to show this in exam, but I'm going to use different color to show you the number version before we go through the algebra. So this is the number version. Okay, so there's the number version. Okay, when I learned this, I remember my uni tutor tell me this is a dummy version. Wow. Don't worry, I'm not going to call it dummy version, this number version. So what we can say, imagine, now this was not in a scheme of specification before 2017. So, but the reason they expose you is because whoever is interested in doing maths in high level, in uni level, they must be aware that this is the level that they are used to. It's a really different kind of maths. Think about GCSE maths compared to A-level maths. That's way different. They're just completely different. Same with university level of maths. They are just completely different league. So imagine, okay? So imagine, okay? In my own little own world, my little own brain, I say, imagine 2, 3, 5, 7 is the full list of prime, okay? Someone tell me 11 is a prime, I don't care. In my own world, there are only 4 prime numbers. 2, 3, 5, 7. So it's a full list of prime. Okay, so I'm saying this is a full list. There's a finite amount, and the finite amount is just 4. Okay, full list of prime. So using his trick, I will let x to be. Okay, so my x value will be x equals 2 times 3 times 5 times 7 plus 1, which is 211. Now, what's wrong with this then? Okay, so the question is, is 211 a prime? Not a crime, a prime. Now, if the answer is yes, then straight away, a slap in my face. This is not a full list of prime because we said 2, 3, 5, 7 are all the primes. So 211 cannot be a prime. So yes, so if it is yes, then a contradiction straight away. Okay? Because 211 not in 2, 3, 5, 7 list. Okay, so therefore no one will talk about yes. Okay, so what we focus is the no part. So is 211 prime? No. Now if 211 is not a prime, then okay, if it's not a prime, then 211 must be divisible by a prime that is not on the list. Now, why? First of all, recall knowledge in GCSE. You have learned to write all numbers in product of primes, remember. For example, 18, you can write 18 equals to 2 using quick maths. That's 2 times 3 squared. Or 26, that's 2 times 13. Or 300, oh, that's a difficult one actually. I don't know why I put myself in this position. That's 2 squared times 5 squared. That's 25 times 400 times 3. Okay. Now, any numbers could be written as a product of prime. Now, 211 cannot be divisible by 2, 3, 5, or 7. That means when we write 211, there couldn't be a 2, 3, 5, or 7 into it. Why? Because of the plus 1. That's why it's genius. Because 211 divided by because 211 divided by 2, 3, 5, or 7 will have remainder of 1. That's why it's a genius, plus 1. We'll have the remainder of 1. That's why they're not divisible by 2, 3, 5, and 7. Okay, so if 211 is not divisible by 2, 3, 5, and 7, and it's not a prime, then surely there must be another prime that comes to help decompose this 211. I'll give you an example. Let's say the number 143. Now 143 is not divisible by 2, 3, 5, 7. Let me ask you a question. Do you think 243 is a prime? You can try it. The answer is no, it's not a prime. Because even though it's not divisible by 2, 3, 5, and 7, we can still write as 11 times 13. These two are primes. So what I'm trying to say is, if 211 is not a prime, then it must be divisible by a prime that is outside of 2, 3, 5, and 7. In the case of 143, it would have been 11 and 13. So, therefore, let's go back to this number version or dummy version. Then 211 must be divisible by a prime that is not on the list. Again, contradiction. Okay, so that is the whole understanding of it. So either way, even though 211 is prime or not prime, they will both lead to a contradiction for different reason. Okay, if 211 is a prime, then straight slap in my face is a contradiction because it's not a full list. You say it's a full list, but it's not. You lied to me. If 211 is not a prime, then there must be another prime that could help go in. That must be 211 must be divisible by another prime that is not on the list. Again, another slap in my face. So contradiction. So let's carry on with the algebra version. So I'm going to carry on writing in blue. That means that's what we write after the word let x be a number, such that in here. So back to the proof. Okay. So write in blue. Okay. Now, since x is not divisible by p1, p2, p3 up to a pn, you can write because remainder is 1, you don't have to write this. It's just for understanding, because remainder is 1. Therefore, and since x not n and x is not a prime, you cannot assume x is a prime. So therefore, what we're trying to say in here, x not a prime, we're going through to this root that say no. So if x not a prime, then therefore x must be divisible by a prime number that is not on the list. So therefore, P1, P2, P3, or the Pn is not a complete list of prime, and therefore contradiction. Why contradiction? Because we said there is a finite list of prime. We assume there is a finite amount of prime numbers, and this is the full list. So we have slapped our own faces. We said, actually we found that's not prime, therefore contradiction. Therefore there is an infinite amount of prime. Now I'll suggest you write it down and try to understand it. And then before the exam, I'll remind you to go through it again, because that's when the student try to record the knowledge again. But you must write that. You must write out in a way that you must understand what's going on step by step. Okay? And that's the end of chapter 1.1. Thank you.